Now that we've discussed variable selection in the previous lecture, we're going to actually apply it using the R programming language. So for this exercise, we're first going to load in 3 libraries. First one will be mass, M-A-S-S, all capital, and if you haven't installed that, you should go up here to packages and select your repository and then install the mass package. But let's just select these guys. And now we're going to use one of the predefined data sets that are included with R. And this is going to be Motor Trend Cars data set. And I always like to take my data sets and load them into just a variable that I like to call DF for data frames. That's just my personal best practice, but you don't need to do that. So I'm going to work with DF. Now, if I type DF, you can see that we have lots of different cars, and we have their miles per gallon and cylinders and a few of the other variables. I'm not even sure what some of these variables are. But if you don't know what variables are for the predefined data sets, you can type question mark, you can type MT cars, and let's take a look. So we can see here that we have miles per gallon, the number of cylinders in the car, and that is for the engine. Displacement, I'm not sure what that means, but gross horsepower, rear axle ratio, weight of the car, quarter mile, that's probably the amount of time it takes to go from 0 to a quarter mile. These are just basically variables that you can use. And what I want to do with this data set is I'm going to try to predict the miles per gallon. So this is the fuel efficiency. So we're going to build some models for that. So for this, we're going to use variable selection. And this will be the techniques that R will, provides for you. And in order to do that, we're going to need to create 2 models. The first model, I'm going to call this thing the upper model. And you could name it anything you want, but my convention is I call it the upper model. And I'm going to include every single variable. So I'm going to predict MPG, miles per gallon, and I'm going to use all of the variables. And this is the data set. And then over here, I'm going to predict the lower bound. And this is only going to have no variables. It's just going to have, when you give it the number 1, what you're saying is just take the average, and that will be it. So this is going to be a model that has no variables and just has an average. And this has all of them. So let's run both of those guys real fast. And if we look at a summary of them, let's look at the summary of the upper model. And you can see this is all of the variables predicting miles per gallon. And if we look at the other one, this is the one that only predicts the average, which in this case is 20 miles. In other words, this guy here is just saying, I don't care anything about the cars. They have an average miles per gallon of 20 miles per hour or per gallon. Okay, so we're going to use these guys for variable selection. And the command for that is this guy right here. So LM, linear model, that is the command that will do the regression. This guy right here, step AIC, is going to do a forward, backwards, or a stepwise selection, and it's going to decide on the best model using the AIC metric. And if you recall, AIC is one of the 3 metrics we discussed in the previous video, where the adjusted R-squared, the AIC, and the Schwarz-Bayesian criteria. So this one here is going to try to find the lowest AIC value. And what we will do is we're going to give it several different parameters. The first parameter is we say, what is the starting point? Well, in this case, we're going to start with nothing, the lower guy. So this guy has no variables. So we're going to start here, and we're going to go forward. This is going to be forward selection, and we are going to tell R that the scope of our model should be somewhere between having no variables and having all the variables. So he's going to look for everything. He's going to start with nothing, and he's going to look for the best model from nothing to all. So I'm going to call this guy the new linear regression forward selection. So let's run him and see what we get. And it gives us all this output. So what happens here? Well, right now, R starts with just an empty model, and it tries to just add the weight only. If it just uses the weight, it has an AIC value of 73. If he uses only the cylinders, he has an AIC of 76. And the displacement, he has 77. So he looks at all of these, and the best variable, the one with the lowest AIC, is using weight. So he's going to now say, okay, I'm going to use weight, and the weight has a 73 AIC, and that's better than the AIC of having nothing. So we got the best guy. Now he says, okay, what if I add cylinder? That's the new AIC is 63. Horsepower, it's 63.8. Q-sec, 63. So he tries a second variable, and the best one is cylinders. So now the best model for predicting miles per gallon is weight and cylinders. Now he tries again, and incidentally, the AIC is 63. That's better than 73, so we're getting better. So now we're going to try one more time, and he tries everybody again, and he gets horsepower. So now we have weight, cylinders, and horsepower, and look, my AIC got better still. And then doing nothing was the best model. So in other words, adding AM to the model would make it worse, 63.44. That's worse than this guy. So at this point, R knows to stop. So this is the best model according to the forward selection. So if we do a quick summary of this thing, we can see that if we want to predict miles per gallon, we start with 38 miles per gallon. And for the weight of the car, that's going heavier the car, the less miles per gallon. That makes sense. Cylinders, the more cylinders you have, the worse your gas mileage, and that makes sense because the cylinders are how powerful are your engine. And the horsepower, again, lots of horsepower, not a lot of gas mileage. And we have an R-squared of 82. So this guy here is our model that we get from doing forward selection. Now, how do we do a backward selection? Now, the backward selection starts, we're going to call this guy new linear regression backwards, B for backwards. Now, this time we're going to start with everybody. And we're going to go backwards. And the worst model, or the smallest model, would be no variables, and the biggest model will be everybody. So let's do that. And here we go. And you can see that we start off with everybody, and when he removes cylinder, the AIC goes from 70 down to 68. So then he says, okay, we got all this stuff. What about if we remove VS? And we get another, even a better model, 68 to 66. Then he removes carburetor. And it goes from 66 to 65. Then he gets rid of the gears. It goes from 65 to 63. And then we go down here again and we get rid of the displacement and we go from 62 to 61. Then we get rid of the horsepower and we go to 61. And eventually we have, incidentally, I think this is the same 3 as before, weight, Q-sec, and AM. Let's see if that's the same as up here for the other guy. Weight, no. The forward selection gave us weight, cylinder, and horsepower, and gave us an adjusted R squared of 82. This guy gives us weight, Q-sec, and AM. Is that it again? Let me just look one more time. Weight, Q-sec, AM, and up here it was weight, cylinder, and horsepower. So yep, this is a completely different model. So going backwards, we come up with these 3. And if we do a quick summary, let's see what that is. '83. So this is a slightly better model. Does it make sense? Well, this guy here, the heavier your car, the more likely is, your your car is heavy, it's going to get worse mileage. Q-sec, I'm not sure if this, apparently the more the Q-sec, the better the mileage. I don't know what AM is again. Let's just take a quick look at AM. AM is transmission, automatic. So if you have an automatic transmission, or no, a manual transmission, so this is where you manually adjust the gears. If you have a manual transmission, you get better gas mileage, and I think that's true. So okay, there we go. So we get a different model. Now what happens if we can do forward stepwise and backward stepwise. So for the forward stepwise, we're going to start with nothing, the lower guy. We're going to go in both directions. We're going to add and delete variables, and then our final model will be something like this. It either has no variables or all the variables or something in between. So let's try that real fast. And here you can see we start with one variable, with nothing, and we add weight, and then we try adding all the variables, and then we even try to take some of them out. And eventually we go to cylinder, and then we get weight, cylinder, and horsepower. So that was the same guy as we got with forward selection. So there you have it. We could, of course, do a quick summary of that model. And just to be complete, we could do the stepwise in the other direction, where we start with everybody, we go both directions, and we're going to have it be anywhere from no variables to all the variables. And let's see what we get with that one. And this one we have weight, Q-sec, and AM. So that's the same as the backward one. So there you go. So that is how we can do variable selection. Now, interestingly enough, we can now do some predictions. And let's use this guy here, the first one. And let's make a prediction. And let's look at our errors. So let's do those. And let's plot. Let's see if our model was any good. And that looks pretty good. It's a nice, the true mileage is here and our predicted one is here. Looks pretty good. Okay. And let's look at this guy right here. This will be the errors, and we want them to be scattered all over the place. And that they look pretty scattered to me. I don't see any obvious patterns. Therefore, we're going to assume that there's no we're going to assume that there's no pattern in the errors, and therefore it is homoscedastic. And now, what else could we do with variable selection? Well, the kind of a neat thing about this lower and upper is we can force the model to have certain variables in. We could say something like, okay, we're going to start with, instead of all the variables, what if we started with cylinder, displacement, horsepower, and carburetor? So we're going to say all of these guys. And we're going to say that the lower one has carburetor. So what's going to happen here is the final model will only have at most all of these, and it will have to have carburetor. So it's going to have that guy at least. So there's no way carburetor won't be in the final model. So let's try this. Whoops. Okay, so we've got two models here, and let us just do a quick summary of both. Now these aren't I'm just throwing these numbers out, or these variables out there. I don't know if these are going to be good models or not. But okay, we got two models. This one's got an R squared of 75, and this guy's got an R squared of 28. So we're going to build a model using these guys, and it's going to have to at least have this guy in the final model. Okay, and let's do a forward selection. Let's start with the carburetor and go up to the other guys, and let's see what makes it into the final model. And the final model has carburetor and displacement. So those are the two variables, and we've got a 75 R squared there. And so that's, just if you want to force specific variables into a model, you can do that. Now, let's do one other thing here. Let's use a decision tree for variable selection. So how do we do that? Well, the first thing we're going to do is we're going to go back and build a decision tree using this mile. We're going to try to figure out the miles per gallon on the decision tree. And let's just see what we get. So let's build this decision tree, and we're going to predict miles per gallon. And I'm not sure how good this model is going to be. There we go. So we start off looking like this, and 20 miles per gallon, and we come over here and we get, if you've got lots of cylinders in your car, your mileage goes down. Lots of horsepower, the mileage goes down. So there we go. We got a real simple model here. Now we're going to ask the decision tree, hey, decision tree, what variables do you think are important? Now, if we look at this data set, you can see we've got 10 variables here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got 10 variables that we could predict miles per gallon. So we're going to ask the decision tree, what variables did you like? And so of the 10 variables, the decision tree says, I liked these guys: displacement, horsepower, cylinders, weight, Cusack, VS, carburetor, and gear. So that's 1, 2, 3, 4, 5, 6, 7, 8. So he likes 8 of these guys. But if you look at the number underneath, the bigger this number, the more important the tree thinks it is. So This guy's got 35, 35, 34, 28, 21, 18, 1, and 0.9. I'm not even going to use the carburetor or the gear. I'm just going to use these guys right here, the first 6. So we ask the tree, and the tree says, I like these 6. So I'm going to build a linear model, and I'm going to say I'm going to predict miles per gallon using 1, 2, 3, 4, 5, 6, these 6 variables. And let's see what we get. And let's do a quick summary of this. And we get an adjusted R squared of 81.45. Not sure if that's the best model in the world, but this is the model we got. We got a pretty good model here, though. I mean, 81, that's not too far off from the other guys. The other guys were like 82. So this is a pretty good model. So trees can sometimes do a pretty good job. You can also, well, let's see how, if this thing, let's do a predicted variable, and then let's do the error distribution. Let's see if both of those, how that's performed. Okay, so let's see. Let's plot this and see if the model is any good. And looks like a nice diagonal line, so probably the model is good. And let's take a look at our errors and see if there's any. And that looks pretty random. So, okay, I'm going to say that this is probably a pretty good model. And one final thing you could do is you can combine these things. So you could say something like, okay, I'm going to use the decision tree variables right here. And then I'm going to do a stepwise selection to make this smaller. So what if we were to say, okay, let's start off with the tree variable here. And we've got these 6 variables. And then we say, okay, and then the lower level, no variables, just a single average. And then I'm going to say the new linear regression, tree and stepwise combined. I'm going to start with nothing. So I'm going to start with this guy. I'm going to go in both directions. And I'm going to find a model between having no variables and all of the variables that the tree liked. So let's do that real fast. And it likes weight, cylinder, and horsepower. It seems like it keeps going back to those 2 guys, or those 3 variables all the time. And, well, we know how this is going to do since we've already seen this before. And there we go. And let's try it again. And those are error distribution. And again, it's random, so we can assume that this is a pretty good model. Okay, so this is, again, how you would use variable selection with the regression. Again, you're going to need to create 2 models, one for the high end of the most variables you would want to use, and in this case I'm using all, and then a lower level of 1, meaning just take an average, no variables, just take an average, and then you're going to do a stepwise selection, and you give it which one do you want to start with, and you can even say, forward, lower level, upper level, whatever. You can, and you can give them these options, and then that's how you can find the variables to use. And again, this is a trivial example. There's only 10 variables, and it's pretty easy. In a real world situation in the corporate world, you will probably have hundreds of variables to work with. So the importance of variable selection is becomes more apparent then.